looks like it's about that time. Well, you can ask Cheyenne. He's the
He's like really slow. All right, you're gonna point. Yes. Until like later on. He had a dinner meeting and he said he might stop by one next week. Depending on when that is. We're supposed to have a meeting this week or soon. Yeah. Kind of get facilities together and get on board with the new exciting. Yeah, I'm looking forward to that. Yeah, there's a lot of things we can do. The university's already behind it. We are.
And the timing's been perfect. This is exactly what we need moving forward.
How you doing? Good to see you. Great. Yeah, this is pretty exciting. Thanks for coming by. Okay, good evening. I think we're going to go ahead and get started. A couple more people grab their seats. We have some exciting new announcements tonight and some students that have worked crazy hard for the past year to put this together. My name's Stefan Duma. I'm director of ICTAS, which is one of the groups that's going to support these students moving forward. It's a great pleasure of mine to be here tonight to introduce Hyperloop and a neat thing they're going to show you in a few minutes. Like I've said, they've worked hard for about a year to do this. It's already an impressive feat, but the excitement doesn't stop here. One of the things that we can talk about tonight for the first time is a brand new announcement to help complement this impressive team. On behalf of Virginia Tech's Provost Office, the College of Engineering, and ICTAS, we are going to be funding the construction of a test track for Hyperloop to use in the development of their system. It'll be the first one built on the East Coast as part of our broader structures. This is part of Virginia Tech's broader intelligent infrastructure announcements that you've seen over the past couple weeks. With this new development, I'm confident the team will make technological breakthroughs the world has never seen before. Team Hyperloop's a perfect example of the VT-shaped student concept, where you combine deep knowledge in a discipline with cross-cutting skills in communication and project management. We are proud of this team's success and involvement in reinventing transportation on a global scale, and the impact Virginia Tech has in educating students to solve complex 21st century problems. With that, I'm excited to introduce and welcome Cheyenne Malik to come forward and, as project manager of Hyperloop at Virginia Tech, and present the rest of the program. Cheyenne.
All right, thank you, Dr. Duma, for the introduction and the announcement of building our test track. I think this is the perfect timing as we move into our testing phase. Good evening. My name is Cheyenne Malik. I am a senior in mechanical engineering. I'm the project manager of Hyperloop. All right, so to begin, I'm sure a lot of you already know what Hyperloop is, but for those who don't, I'd like to just kind of give a brief overview of what we're doing. So Hyperloop is a new form of technology that will allow people to travel at very high speeds in a near vacuum to reduce air resistance. And so what that will allow is for passengers, supplies, and any type of cargo to move from point A to point B in the most efficient and quickest way possible. And so some of the locations for implementing a Hyperloop is like from LA to San Francisco. And so that 6-hour car ride you would be able to do in about 30 minutes. And I say we should do it from Blacksburg to Washington, D.C., so we don't have to go on 81 and wait 4.5 hours. Yeah. And so when SpaceX and Elon Musk had announced or released the white papers for this idea in the summer of 2013, this generated a lot of traction and interest in a lot of student organizations, universities, and also external companies. And so last year, SpaceX used this to open up a competition for a Hyperloop pod. And so what they're doing is they're going to be building a test track, and they're doing this as we speak. And in January, we're going to be testing at their test track. And so a little bit of a timeline from where we came from to where we are now. In June of last year, after the announcement, there were 1,200 teams entered into the competition. And in November, we had a preliminary design review. And from those 1,200 teams, we brought it down to 120. And those are the people who competed in the design weekend in January. At January, Virginia Tech placed really well. We were top 5, and we placed 4th place, which allowed us to move forward into the next phase, which is the build phase. And so over the past few months, we've been projecting ourselves and making sure our testing, designs, and any type of our subsystems are optimized. This has been a tremendous experience for everyone on the team. We've learned a lot from laying up carbon fiber to how magnetics works, eddy currents. And so now, over this summer, we've been working on building this pod. And let me tell you, it's not easy manufacturing a Hyperloop pod. But with committed passion and dedication, we've been able to produce what we have here. And so that brings us to today, which is our pod unveiling. This is an exciting time for both us and the Hyperloop team. And over the next few weeks, as Dr. Duma had mentioned, we're going to be doing a lot of testing. And so that involves subsystem testing, full integration testing, and full track testing. And so with the support of our sponsors, the university, I think we can definitely have a competitive pod, and we will be very competitive in January on competition weekend. And so before I introduce our mechanical sub-team, we have about 33 undergraduate members on the team. We have mechanical, aerospace, electrical, software, industrial system, and we also have representatives from the Pamplin School of Business. And all these members have put in countless hours to make this happen. I'm very proud of each and every one of them, and I'm honored to be working alongside each of our members. And so with that, I want to introduce Emir Shimanovic with the mechanical sub-team.
Hello, everyone. I'm Amir Shimanovic. I'm the lead mechanical engineer here at Vhyper, and this is my mechanical engineering sub-team. I like to think it's the best sub-team. We're the largest sub-team. We have 15 members, and we work on everything from the frame, braking, suspension. We work on test rigs. We work a lot with the aero sub-team. We work a lot with the electrical sub-team. We work on mounting for them. We work on anything they need manufactured. So that goes into a little bit of our responsibilities. For this talk, since I don't want to bore all of you with all the details with every single thing we do, I'm going to mainly be focusing on our most complicated systems, which are suspension and braking. But before I get into that, I really want to thank everyone on this sub-team. They put in a lot of hours, a lot of hard work, and without them, this couldn't be possible. Everyone here did a great job, and they're the best team I could ask for. So going to that, we're going to start off with suspension. But before I can even talk about, Before I can even talk about that, we really need to talk about magnets. So for both systems, braking and suspension, everything's magnetic based. So as Sean said, we're trying to minimize drag in every way possible. That includes friction. So what that comes down to is we do not want to touch the track. We have magnets allowing us to levitate and hold us away from the track vertically and laterally. So what you can see here is the magnet housing for the suspension. And our magnets for both systems are based off of two things. That is eddy currents and Hall back arrays. And how eddy currents are is when you have a magnetic field going across a semiconductive material, that in turn produces a current, the eddy current. That eddy current also produces a magnetic field in the opposite direction. And what that allows us to do is it produces a force, and that force can be either a lift or drag force. But based on how we orientate our magnets, which is the Hall back array, you put your magnets in such a way that it magnifies either lift or drag. So for suspension, we want to maximize lift. So we have lift from above for levitation, and you can't really see it here, but these are the wheels to the housing that goes in laterally to prevent us from hitting the side of the rail. So for levitation, we have, this is the housing for the magnets. And once we get up to a certain speed, the magnets propel us upward, and we have wheels just in case we touch the track in any way, and for just starting off rolling because you aren't levitating right in the beginning. On the inside, we have almost the same we have a different orientation, but what this does is this is our lateral stability, and this keeps us from hitting the side of the track. We also have wheels, so just in case we hit the side of the rail. But we also have 6 sets of suspension now. So this is just a view of one, and on the other side, you can kind of see the mirror of the other one. And by having 2 lateral stabilities against each other, that maximizes the lift force. Go into the next thing. And now this is a picture of our braking system. I know it's tough to see, and afterward, if anyone wants to come talk to me about it, we can. But this is, our braking system is actually relatively simple. It's kind of like a caliper on a car almost. Well, we have a pneumatic system because to get the force output we needed at that speed, going electrical would be very difficult. The actuator size would be huge. But as you can see here, this is the pneumatic actuator, and it's very small. So all this does is has a little piston basically that goes forward 2 inches, and it pushes on a load collector. And this load collector is riding on a rail. So the rail goes forward. It would go forward in this direction. You can't see it. But it goes forward, and it's attached to 2 control arms. Now these control arms right there, you can see them a little bit, attached to the calipers. And all this does is pinch in the brakes in and out. And just like a caliper on the car with friction, by bringing the brakes in with our Hall back array, that produces a big force. The force is proportional to our motion, so at very high speeds, we get a large braking force. And as we're slowing down, the braking force is actually decreasing, which is really nice because it gives us smooth deceleration. Cool. That's really all I want to talk about now. Everyone in this team is willing to talk about any of the other subsystems, but for right now, I'm going to hand it over to Keith Baum and the Aerospace sub-team.
Hello, my name is Keith Baum, and I am the lead aerospace engineer here for this team. I'm a senior in aerospace engineering currently, and this is the propulsion and aerospace team with me. And just like Amir said with the mechanical team, I just can't thank them enough. Many of them gave up their entire summer to help get this together, and it would not have been possible without them. Okay, so when we started with the design of our pod and our skin, we researched and we took inspiration from other vehicles that are currently built to kind of get an idea of what we wanted the vehicle to look like. We looked at bullet trains such as the Shinkansen and the Bombardier, and through that we took multiple designs and we ran them through both CFD and through the constraints that we both placed on ourselves and that the Hyperloop competition put on us. These were mainly to make sure that the skin both fit in the frame, that, as you can see, the dummy would fit inside of the pod, to make sure our propulsion system would fit inside of the pod. And after narrowing it down, we picked the current design that you'll see very soon. And as you can see, we have 2 of our early designs in CFD. And so the skin itself is made out of carbon fiber. It has 4 layers. We were able to lay it up ourselves. And we also were able to take the molds that we used to lay up the carbon fiber, and we created those ourselves as well here at Virginia Tech. And what we did with the carbon fiber skin is we broke it up into multiple panels to both allow us to manufacture it easier and to allow us to remove them whenever we need to work on the pod. And so in terms of our propulsion system, the Hyperloop design competition itself does not require a propulsion system because SpaceX provides a pusher which will give every single pod the same initial acceleration. But the pod competition also says that the fastest pod will win, and we want to win the competition. And we also want to distinguish ourselves from the rest of the competition. And so our propulsion system was based off of a cold gas thruster, which is a propulsion system used primarily on spacecraft and satellites for short amounts of thrust, and also for its simplicity as opposed to other forms of propulsion such as a compressor or like a jet engine. And so, as you can see in the picture, our propulsion system is very simple. It consists of primarily our spherical pressure vessel, and then to the left and right we have multiple valves for both filling, for initiating the propulsion system, and also for safety. And so in terms of safety, we have multiple redundancies in place. We have constant pressure monitoring. We have a relief valve to ensure that we don't overfill the tank. And then we have a certified ASME pop valve, which will, in the case of overfilling, will prevent the tank from becoming overpressurized. And then on the right side of the pod, towards the end, we have a hose that will connect to our nozzle, which is currently a converging, diverging bell nozzle, which was specifically designed to both work in a vacuum and optimize our thrust. And so when we are also going to be using nitrogen as our propellant because it is both lightweight and has a very high specific impulse, which means that for its lightweight, it can produce a large amount of thrust. And after both CFD and a lot of analysis, we theorize that it's going to produce about 3,000 newtons of thrust, which will, in addition to the pusher interface, which is going to give us about 350 miles per hour, we're going to get an additional 100 miles per hour, giving us a final speed of about 450 miles per hour. And with that, I'm going to hand it over to our software lead, Brian Elliott, and the software and electrical subteam.
Thank you, Keith. My name is Brian Elliott. I'm a senior in electrical and computer engineering, and I am the team lead for the software and electrical sub-team. I'm super excited to be here tonight. We've been working tirelessly for the past few months to get this ready to show you all. I just want to give a huge personal thank out to our team. These guys have been really killing it over the past few weeks. A lot of these people were new this semester, and I have to say on a personal note, I've been so impressed with the level of work that they put into it. It's really hard to jump into a project in the middle of something and catch up really quickly, but these guys have jumped in feet first and just taken on roles that none of us saw them filling. So thank you guys. So some of our primary responsibilities on our team is distributing the power systems, writing the control software, writing the communication software, and also interfacing with all of the magnets. So there's a number of different subsystems on our pod that we utilize. The first one being the navigation system. Our navigation system is crucial to our pod. It tells us exactly where we are inside the test track at all times in real time. That's super important because at the top speeds that we're going at, there's no time for error. You need to make decisions on a split second, and you can't rely on a human being to be able to push a button and control things. Our navigation system utilizes a couple of different things to tell us that position. between the optical markings inside of the test track, as well as also a number of other sensors that provide us more real-time data. Our communication system links our pod to the outside control station. This is super important for us as well because once you put the pod inside a vacuum, it is no longer accessible by a human being. So we need to be able to control our pod from outside of the track and still be able to start the test run, control the propulsion system, control the braking, and do any other minor things that we may need to do. As well as that, we also relay all of the data that we collect on board to the outside control station so that we can record that and see what's actually happening inside of that test track. Next up, we have our levitation system, which they've already told you a lot about tonight, so I won't tell you more. But we have a number of sensors on board that tell us exactly how far off the track we are, which we can use to determine our pitch and roll. And if we do start to see any kind of fluctuations that are bad, we can bring the pod to a complete halt. Our stability system, similar to the magnet system, we also use that to tell exactly where we are. We go ahead and use that so that we have a nice, safe, and comfortable ride. We don't want any rocking on our pod once we apply the brakes or when we apply the propulsion system. If we start to see any sort of major instability on that as well, we can also bring the pod to a complete stop. That way we don't damage the track or our pod. Our propulsion system is probably our most important system on our pod. It's very cool. It's the only team that we know of that has this kind of a system. But with it comes a lot of very interesting things as well. You have to be able to actuate it on a very precise time. With the pusher interface, we are not allowed to actuate that propulsion system until we go ahead and release from that pusher interface and have some separation from it. At that point, we'll activate the propulsion system, which will provide us with additional thrust to continue accelerating us so that we'll have the highest top speed. And just as important as turning it on is the ability to turn it off. Without the ability to turn it off, we would just continue rocketing into the end of the track and crash. Finally, probably the most important system out of all of these is braking. With all these other things, we still need to be able to stop the pod. If we can't stop the pod, then it's just going to crash into the tube, and it's going to be for nothing. Thank you very much. It's now my pleasure to introduce our business team lead, Laura Walensky.
All right, thank you, Brian. Well, good evening. Thank you so much for coming out. My name is Laura Walensky. I am a junior, double majoring in business information technology and finance, and I'm the financial controller for Hyperloop at Virginia Tech. This is Chris and Manib. They're two of our students from the ISE program, and we make up the business sub-team together. So the business sub-team started off as more of a branding thing, wasn't supposed to be long-term, but as it went on, things kind of grew into, we started to fulfill more roles. These roles include things like bookkeeping, purchasing, inventory management, process improvement, just doing anything that the engineers need to get this pod done. All right. So first, we would like to, on behalf of the entire team, we would really like to thank our sponsors. Because of our sponsors, we were able to take a drawing on the back of a napkin and turn it into the reality that you are about to see tonight. So I would like to call for a big round of applause for our sponsors. So there are a few more thank yous we would also like to extend. First off, we would like to thank our faculty advisors for always being there for us and giving us all the support that we need. We would also like to thank Lindsay Hawk and the rest of the PR crew for helping us pull off this event tonight. And last but certainly not least, we would like to thank the Virginia Tech community for rallying behind us from the very start. We are very proud to be Hokies, and we cannot wait to represent the university at competition in January. So thank you. And with that, I would like to welcome our faculty advisor, Pat Artist, to the stage.
Good evening. 55 weeks ago, 3 students I had never seen before walked into my office and said they needed an advisor for Hyperloop. I said yes. I went over and immediately talked to Dewey Spangler, who joined us. Rob Parker joined us this fall, and it has been a great ride. But I have the pleasure tonight of saying, let's unveil the pod.
Good. Looks good. Does look good. No.